The work I am going to present is joint work with Safarazadeh on certain classes of bounded maps on non-commutative LP spaces. So let me give the general framework. So non-commutative LP spaces are objects which are defined usually sometimes on general phenomenon algebras, but here I will restrict to semi-finite phenomenon algebras. So I take M, a semi-finite phenomenon algebra, which means that it can be equipped with a normal semi-finite faithful trace tau. And for any p strictly between 1 and infinity, I let LP of M denote the associated non-commutative LP space. So what does it mean? Depends, of course, if you are familiar or not with this topic. So some kind of formal definition is this way: if M is your phenomenon algebra and if M acts on some Hilbert space H, then there is a set of star algebra of measurable of operators, which are usually unbounded operators acting on H, denoted by L0 of M, and called the measurable operators. Of course, I do not give all the definition, but I will try to give some kind of intuition about that. And so these are some operators, maybe possibly unbounded operators on acting on H. And the LP space associated with M is a space of all such operators A for which the trace of the pth power of the modulus of A is finite. And this is a Banach space for the norm defined this way. So P norm of A is you take the trace of modulus of A to the power P and you take the 1 over P power. So this, of course, this definition is supposed to be modeled on the classical definition of LP spaces that you recover when you take for M an infinity space associated with a measure. And in this case, the trace is just the integration. The simplest class of non-commutative LP spaces, which is not the classical LP spaces, are the so-called Shatton classes that you certainly all know. Shatton classes are these operators on B of L2, which satisfy this definition, but with tau being the usual trace on B of L2. Okay, so the idea of non-commutative LP spaces is to give a framework to study operators like functions, but with the spirit of all what happens on commutative LP spaces, like studying sequences of operators, semi-groups of operators, and so on. Very soon we will consider what is called the L1 valued space LP of M L1. So L1, of course, is a space of absolutely summable sequences. I will give the definition a little bit later, but I just want to say in this introduction that this is a completion of a tensor product of LP of M and tensor L1. And with this definition that is going to come very soon, there is a notion of L1 boundedness. So we consider two phenomenon algebras, M and N, and you consider a linear map from LP of M into LP of N, and you consider the following definition. You say that T is L1 bounded if T tensor identity of L1, originally defined on LP tensor L1, extends to a bounded map from LP of L1 into LP of L1. So, of course, this extension is unique if it exists. And in this case, we will denote by norm of T sub L1 the norm of this extension. So this property is a tensor product extension, which is some kind of very classical thing in operator theory. You want to tensorize things and so on. And a little bit more definition, we will say that T is L1 contractive, is this L1 norm is smaller than 1. Okay, so what is the plan of the talk? The plan of the talk is, first I will remind you, or I will give you the definition of LP of ML1. And once you have the definition of LP of ML1, you have the definition of L1 boundedness. The second part of the talk, I will relate L1 boundedness to some kind of classical notions, positivity of maps, regularity of maps. I will explain this a little bit in this part of the talk, and I will in particular mention some questions that I consider as interesting questions in this context. In the third part of the talk, which should be considered as the main part, I will relate L1 boundedness to L2 isometries. There is a theorem about isometries on LP, on non-commutative LP for P different from 2, which is known as Yeadon's factorization theorem. And I will discuss the validity of this theorem for P equal to and related to L1 boundedness. And in the fourth part, I will introduce some notion of S1 boundedness, where S1 is the trace class replacing L1, and I will consider related questions. Okay, so the first part is what is LP of L1? So this definition, as I will explain, goes back to Marius Junger. So let me come to this. Okay. So first, let me remind you what happened in the commutative case to give you the right intuition of what is going on. In the commutative case, you start with a measure space. For any Banach space, you have the definition of what is called the Bochner space, LP valued in E, which is the space of all classes of measurable functions from omega into E, such that this quantity is finite. So we require the norm, we require the norm function of F to be in the classical LP. This is the definition, and this is a norm, and this gives the definition of the Bochner space. In the particular case, when E equals L1, you get the definition of LP of L1. So you get the definition of LP of L1 in the commutative case this way. But because L1 is a space of sequences, you can write an alternative definition. So in the case of L1, you can say that using the coordinate functions, you can regard LP of L1 as the space of all sequences xn in LP, such that this quantity is finite. So this quantity here, you recognize the L1 norm of the sequence of functions. So this corresponds to this quantity here. So this L1 norm is the LP norm of the sum of these functions, provided that this is finite. So this is the definition of LP of L1 in the commutative case. Of course, you can do the same with LP of L2. You can define LP of L2 as a space of sequences of LP such that this quantity is finite. So for anyone familiar with non-commutative analysis, you know that when you want to extend this definition to the non-commutative case, we get to some difficulties related to the definition of the modulus. So for instance, if you want to make an extension of the L2 norm, you may consider the following. You consider a finite sequence, say, of LP of M, and you may define LP of ML2 this way. So if you compare with the commutative case, it means that we simply replace the modulus of x squared by x star x. But the problem is that in the non-commutative case, x star may be very different from x star x. So you could also consider this alternative definition, but in general, they are not the same and they are not equivalent, except when p equals 2. So defining vector values and spaces in the non-commutative case is very difficult. It's a quite tricky tricky question. So you have similar difficulties if you want to do this with LP of L1. In LP of L1, you could try to consider the modulus of xn, but if you consider the modulus of xn star, it will not be the same. It will not give you the same quantity, the same norm. So this will lead you to some difficulties. So these difficulties were more or less solved in the 90s by Pizier in the case when the von Neumann algebras are injective. So more precisely, when M is injective, Pizier introduced a definition of LPM of E for any operator space E. So I do not intend to define what is an operator space, but it is not only a Banach space. It comes with a matrix structure, so it allows some good definition of these spaces, and this is what Pizier did in this series of papers in the 90s, but only in the injective case. In the general case, by general case, I mean not necessarily injective, Junger introduced a definition of LP of L1, which I will explain in the next slide. It was important introduced it in the process of proving a non-commutative version of Doob's inequality. And in the injective case, Junger's definition coincides with Pizier's one, so everything is when L1 is endowed with its natural operator space structure, which is the maximal one. So everything is very consistent here. And another consistent thing is that in the commutative case, Pizier's definition coincides with the Bochner space definition. So what is Junger's definition, finally? So the definition is this one. You consider Xn a sequence of LP. And we say that Xn belongs to LP of L1 if there are two sequences, An and Bn in L2P, such that for all n, Xn is the product An Bn, and moreover, the two sums of An star and Bn star Bn converge in LP. So this is the definition of LP of L1. And in this case, the norm on this space is obtained by taking the infimum of these quantities over all possible sequences in L2P which satisfy these properties. So this definition, as you see, with the star on the right here and the star on the left here, is quite symmetric, and indeed, the definition is symmetric in the sense that when you consider a sequence of elements of LP, the norm of Xn and the norm of Xn star are the same. So this turns out to be the right definition of LP of L1 for many reasons. So this goes back to maybe 20 years ago. Okay, so this is a space with which we are working on. We were working, and as you can see, because the definition is a little bit complicated, understanding L1 boundedness is not very simple. So this is what I am trying now to discuss in part 2. So again, I start from the commutative case to tell you what is going to make things easier to understand. So in the commutative case, okay, so we consider commutative LP spaces. We consider a bounded operator T. And we say that the operator T is regular if for any Banach space E, T tensor the identity of E, which is originally defined on the tensor product of LP and E, extends to a bounded map from LP of E into LP of E. So this is problem tensor product, tensor extension problem. It turns out these results are quite old, going back to the 50s or to the 60s, so I didn't try to give precise reference here. It turns out that if this property of this extension property is true for L1, then T is regular. And in this case, for any E, the norm of T tensor IE is less than the norm of T tensor identity of L1, which we call the regular norm of T. So said otherwise, L1 is a test space. If the extension property holds for L1, it will hold for all E. In this sense, L1 is some kind of universal object for this question of tensor extension. And the classical result, as I said, going back to the 50s probably, is the following theorem, two parts. The first part is that if T is positive, then T is regular and its regular norm is equal to its norm. This is quite easy. The difficult part of the theorem is the following converse. An operator T is regular if and only if there exist four positive operators, T1, T2, T3, T4, on LP, such that T has this decomposition. So said otherwise, if T is positive, T is regular, it's very easy. The regular maps, it's very easy to see that they form a vector space. So any combination of positive maps will be regular, but the converse is true. Any regular operator will be a linear combination of positive maps. Of course, this kind of statement is sounds very much like Woodstock's theorem about complete boundedness being equivalent to linear combination of completely positive maps, and this is, of course, one reason why I am interested in these topics. Okay, so now let's go to the non-commutative case. In the non-commutative case, again, so I consider two semi-finite fundamental algebras and a bounded operator T between the associated LP, non-commutative LP spaces. Again, in the injective case, Pizier proved some important theorem generalizing the previous commutative theorem. In 1995, Pizier defined the notion of complete regularity by saying that P is completely regular if T tensor the identity of E extends to a bounded map from LP of E into LP of E for any operator space E. And moreover, Pizier proved that T is completely regular if and only if T is a linear combination of four completely positive maps. So this is some kind of LP analog of Woodstock's theorem. Because complete regularity is something which is true for any E, it is in particular true for max L1, for L1. So complete regularity implies L1 boundedness in this injective case. But this is a much stronger property, at least in the except in the commutative case. In the genuine non-commutative case, this is a much stronger property. You cannot expect L1 boundedness to imply complete regularity as it does in the commutative case. So in this context, L1 boundedness appears as an intermediate notion between boundedness and regularity. Intermediate, some kind of diagonal form of complete regularity. Moreover, because LP of L1 is defined for any M, it makes sense in a non-injective case, whereas Pizier's notions make sense only in the injective case. So this L1 boundedness is interesting in itself for two reasons. Okay, so because of the commutative results, now I want to discuss the connection between L1 boundedness and positivity. So the natural questions on L1 boundedness are the following ones. So first question, you take T from LP to LP, be a positive operator. The question is it L1 bounded? And in this case, do we have the equality between the norm of T and the L1 norm of T as we have in the commutative case? The second question is related to the converse, the main result in the commutative case. If T is L1 bounded, the question is, can T be written as a linear combination of positive maps or four positive maps? will be the same. Okay, so here are the results, and let me tell you what is known and what is open. First, I mentioned a natural definition, which is that we will say that an operator T, as before, is 2 positive if its natural matrix tensor extension to M2 by 2 matrices. So you define identity of M2 tensor T on these spaces by the usual algebraic rules, and you demand this operator to be positive, and this is the definition of being 2 positive. So the first result is that if T is 2 positive, then T is L1 bounded, and the L1 norm of T is equal to T. The second result is that if T is only positive, not 2 positive, but only positive, then T is L1 bounded, but we do not get this equality, we get this result. We get an extra factor 4. So the L1 norm of T is smaller than 4 times the norm of T. So this theorem is a partial answer to question 1. But I want to mention that question 2 is open. And for me, it's an interesting question. And let me go a little bit beyond this topic of this talk. Even in the case P equals infinity, for me, it's an interesting question. I mean that, of course, by Wittstock's theorem, we know that in the injective case, we can characterize linear combination of complete positive maps by complete boundedness. And there is this notion of decomposable maps introduced by Hagerup that explains a lot about this, and also Van Paulsen's proof of Wittstock's theorem and so on. But what seems to be unknown is characterization of maps which are linear combination of positive maps, not completely positive, but positive maps. And this is exactly the question 2 in the case P equals infinity. So this is a question I wanted to draw to your attention. Okay, so now let me come to part 3, which is the main part of the talk. This is the reason why we introduced L1 boundedness. Okay, so I remind you first, I recall you first Yeadon's theorem. So Yeadon's theorem is a non-commutative version of what is called Lamperti's theorem. Lamperti's theorem is a theorem describing isometries on commutative LP spaces for P different from 2. Yeadon's theorem is an analog of this in the non-commutative case. So what is Yeadon's theorem? You consider P different from 2, very important. You consider an isometry T between 2 non-commutative LP spaces. We are in the semi-finite framework. The factorization is this one. There exists a normal Jordan one-to-one homomorphism from M into N, a positive operator B affiliated with N, and a partial isometry W in N, such that for any A in the intersection of M and LP of N, T of A is equal to W B J of A, and plus some other properties. First property is W star W is a support projection of B, and last property, every spectral projection of B commutes with J of A for all A in N. So basically, this means that B can commute with a Jordan homomorphism J. So let me remind you that a Jordan homomorphism, by definition, is a linear map that satisfies that J of A star is equal to J of A square is equal to the square of J of A, and J of A star is equal to J of A star. And it is obvious that any star homomorphism is a Jordan homomorphism, and also that any anti-star homomorphism is a Jordan homomorphism. And what is non-trivial, but which is very, very important, is that conversely, when you have a Jordan homomorphism, from M into N, then you have certain decomposition. I don't know if it is necessary that I read all the details, but there is a projection in N and a star homomorphism pi from M into the corner E and E, and a star anti-homomorphism sigma from M into the other corner, 1 minus E and 1 minus E, such that in the 2 by 2 matrix decomposition associated with E, you have this description or this decomposition of G, of J. So the idea is that any Jordan homomorphism can be decomposed in a star convection and anti-star convection. Okay, so maybe I skip this to go a little bit. Okay, so I prefer to skip this to because of the time. So Yeadon's theorem is for LP isometries. It cannot be true for L2 isometries because there are too many isometries. There are too many isometries on L2. This is the same as in the commutative. This is of course already the case in the commutative case. So the question is, a natural question, however, is to be able to describe the isometries of L2 which satisfies Yeadon's factorization theorem. So what I mean is, okay, I'm going backwards. So you look at Yeadon's theorem, and the question is, you consider an isometry T from L2 into L2, in which case does this isometry satisfy all these conclusions? The existence of J, B, and W such that you have these three properties. So this is what I call to have a Yeadon factorization. And the answer is in this theorem. So for a linear isometry from one non-commutative L2 spaces to another non-commutative L2 spaces, the following statements are equivalent. T has a Yeadon type factorization, which means it satisfies the conclusion of Yeadon's theorem if and only if T is L1 contractive. So this was the main reason why we introduced this notion. It was to describe these isometries, and as I told you in part 2 of this talk, it turns out to be an interesting notion for me because it's this L1 boundedness, because it seems to say something about linear combination of positive maps. So I do not want to come back again to this part 2, so let me stick on part 3. So this is the main theorem. Okay, and for instance, by using this characterization, we can recover an old result of Roaz from 66 that a positive isometry as a Yeadon type factorization. Well, this was not written this way, of course, because Yeadon's theorem came after this, but this is a special case. So let me now focus on this theorem 2. So the proof of theorem 2 is obtained by putting together two results. So let me explain it. So yes, I would say that the proof of theorem 2 has two main ingredients. This is the right thing to say, two main ingredients. So first ingredient is the use of separating operators. Okay, so first ingredient. So we say that two elements in LP are disjoint if AB star equals 0 and A star B equals 0. And this is equivalent, and this is maybe more intuitive, to the fact that modulus of A modulus of B is 0, and modulus of A star modulus of B star is 0. In the commutative case, you do not need to make any difference between the A and the A star in this characterization. So in the commutative case, this is equivalent to the fact that A and B have disjoint supports. So this gives rise to a definition about maps, a bounded operator T on LP, which will be called separating if it preserves disjointness. If whenever A and B are disjoint, then T of A and T of B are disjoint. And it turns out that there is a characterization which is exactly the Yeadon factorization. So the proposition is that a bounded operator T, not necessarily an isometry, I mean any operator T. When you take any operator T, T is separating if and only if it has a Yeadon type factorization. So this is the first ingredient in the proof, and it is a theorem, as this is a result of independent interest, of course. And at the time we were proving this, this result was proved independently by Weixin Hong, Samia Rai, and Shimeng Wang. Okay, now the second ingredient. The second ingredient is this proposition, which is some kind of metric characterization of disjointness. So we consider A and B in L2. The result is that A and B are disjoint if and only if they satisfy this inequality. So on the left-hand side, this norm in L2 of n valued in L1 for the pair, for the couple AB, means that here I should have written L1's index 2. I mean, I consider a sequence AB and anything else is 0. I consider only 2 elements in the sequence. And the condition is that the norm of this couple is less than this square function quantity. Okay, so I told you before that in the commutative case, disjointness is equivalent to having disjoint supports. But of course, in the non-commutative case, you cannot use supports, or I mean, there are of course notions of support, but you cannot use this so easily. So the problem was to find some kind of new way to describe disjointness, and this is some what I call metric characterization of disjointness. And of course to show you what is I will not show you the proof, but to show what this kind of inequality means, let me show you the commutative case. In the commutative case, the condition in proposition is the following: you consider two functions. The left-hand side here is the square of the left-hand side. No, sorry. Yes, the square of the left-hand side is this quantity, and the square of the right-hand side is this quantity. So in the commutative case, this condition is the following, and in this commutative case, it is very easy to show that this holds true if and only if the product is 0, just using the classical comparisons between square norms and square sums and sums of modulus and so on. But in the non-commutative case, you cannot use such an easy proof, and you have to do something. Okay, so this is the second ingredient, and now let me show you the proof. Let me show you how to combine the two ingredients, at least to show you what I consider the hard part of the theorem, which is the part where I will explain to you that if you have an isometry which is L1 contractive, I want to show you that it has a Yeadon type factorization. Okay, by proposition 1, it suffices to show that T is separating, so this is the first ingredient. And now let us show that T is separating. So we start from two disjoint elements, A and B. By the second ingredient, proposition 2, we have this inequality. Because by assumption T is L1 contractive, this quantity, this L1 norm of TA, TB is less than the L1 norm of AB, so it implies that this is smaller than this quantity. Because T is an isometry, the norm of TA is equal to the norm of A, the norm of TB is equal to the norm of B. So this inequality can be written under this form. And now using proposition 2 again, the other way, this implies that TA and TB are disjoint. So this is why these two ingredients are exactly the ones we need for the proof. Okay, So let me go now to the fourth part of the talk. The fourth part of the talk is about S1 boundedness. So up to now I talked about L1 the sequences. Now I will consider S1 the trace class operators. So the definition, the first thing I want to introduce is a definition of LP of S1, which is very similar to LP of L1, but the difference is that in LP of L1, we consider sequences of elements in LP. For LP of S1, we consider matrices of elements of LP. So the definition is, you consider a matrix of elements of LP. And we say that this matrix of elements belongs to LP of S1 if there exist two matrices AIK and BKJ in L2P, such that for all ij, the xij can be decomposed as the sum over k of AIK BKJ, and the following two sums converge in LP. So this is very much an adaptation of the LP of L1 norm. And in this case, again, following the model of LP of L1, we define the norm of this matrix as the infimum of these quantities, infimum over all possible matrices of elements in L2P for which this factorization holds true. So this is very much similar to LP of L1, but this is for matrices, and of course it takes into account the non-commutative situation, because of course these two elements. We can mimic the previous definition and say that an operator T will be S1 bounded if T and tensor identity of S1 extends to a bounded map from LP of S1 into LP of S1. We denote by norm of T S1 the norm of the resulting operator, and we say that T is S1 contractive if this S1 norm is smaller than 1. In the case when, so let me come back to Pizier's notion of complete regularity to say that in the case when M and N are injective, S1 boundedness turns out to be equivalent to Pizier's notion of complete regularity. So, this notion of S1 boundedness is mostly interesting for non-injective Von Neumann algebras, because in this injective case, everything we will say about S1 boundedness is more or less covered by the notion of complete regularity of P. So in the general case, in the non-injective case, for instance, the result we have is that any completely positive operator T is S1 bound. So let me remind you here what is complete positivity. It is the same as two positivity, but with positivity of all tensor extensions for all n's. For the extension of NP of Mn of n into NP of Mn of n. So there are some results by Marius Junger about these notions that I did not have place to cite, but some published and unpublished results by Marius Junger on this notion, which he was aware of a few years ago. Okay, so again, I want to say something similar to what I said for L1 boundedness. We do not know in general if a map is S1 bounded if and only if it is a linear combination of completely positive maps. To be more precise, in the injective case, this is true because of this, the fact that this notion is equivalent to complete regularity and because of Pizier's theorem, but in the non-injective case, this is again some kind of mystery question. Okay, now you remember that I introduced L1 boundedness in order to study isometries. So to finish this talk, I would like to come back to isometries. What the notion coming with S1 boundedness is the notion of direct Yeadon type factorization. So you remember Yeadon's theorems, you remember Yeadon factorization. So let's see what is this definition. We say that a bounded operator on LP has a direct Yeadon type factorization if there exists a C-star algebra homomorphism pi, a positive operator B affiliated with N, and a partial isometry W in N, such that you have these three properties. These three properties are exactly the properties which were in Yeadon's factorization. So what is the difference between this property and the Yeadon type factorization? The difference is that we demand that the Jordan homomorphism is a star homomorphism. So we consider the restricted class of operators for which the Yeadon type factorization holds, but with a star homomorphism, not only a Jordan homomorphism. And this notion appeared in some work, maybe not with this vocabulary, but in case it's in a different way. But it appeared in a paper by Junger, Rowan, and Sherman, who showed that for P different from 2, if you consider an isometry T, and if you apply Yeadon's factorization to T, then it turns out that T has a direct Yeadon type factorization, if and only if T is a complete isometry. So I remind you that Yeadon's theorem says that if T is an isometry, then it has a Yeadon type factorization. So their theorem is that the isometry is complete if and only if the J, the Jordan homomorphism, can be chosen to be a star homomorphism. So we can expect similar facts to happen in the case P equals 2, and this is exactly what is going on here in the last. This is the last slide. So the theorem we get. So I take any P, but the most important is that it includes the case P equals 2. If you consider an isometry on LPs, then T has a direct Yeadon type factorization if and only if T is S1 contractive. So you remember for P equals 2, the characterization was Yeadon type factorization was corresponding to L1 contractivity. Direct Yeadon type factorization corresponds to S1 contractivity, which is not completely surprising for people used to non-commutative phenomena. And so this provides a version of the Junger-Rowan Sherman theorem in the case. And the last theorem is, and I will stop after this last theorem. The last theorem is that in the case P different from 2, we can improve by the similar techniques we developed to prove this theorem. We could improve the result by Junger-Rowan Sherman by showing that for an isometry on LP for P different from 2, then the direct Yeadon type factorization is equivalent to the fact that T is a completely contracted, not only completely isometric. And that's it. Thank you very much.